Hello everyone, it's April 26th. Well, the crunch has not ended. It's actually getting worse, and I have to keep preparing for the presentation for tomorrow for the committee meeting. So I don't think I'll have the mental capacity to do the hard one. But that said, we might just churn out another easy one just for the lulz. All right. So first, let's take a look at the problem today. Minimum cost to connect all the points. Interesting. That's a new problem? Oh yeah, it's a new problem. Okay. You're given an array points representing integer coordinates of some points on a 2D plane. The cost of connecting 2 points is the Manhattan distance between them, which is defined by the absolute difference between the x and the absolute difference between y. That's the Manhattan distance. Where a val denotes the absolute value. Oh yeah. Return the minimum cost to make all points connected. All points are connected if there is exactly one simple path between any 2 points. So we have this. So I want to connect. There is exactly one simple path between any 2 points. So any 2 points shall have one path. So what do you mean, like, if we do this, like we have two paths and that's not allowed? So it has to be one path, which means it's like there's no loop, right? If you have a loop, then you have multiple paths. So the connected, no loop, that's a tree, right? So you basically want to build a tree out of this and try to make the cost as little as possible. Where the cost is 4, 3, 4, and this cost is 9. Okay, so how do we address this? Minimum cost. Any point can be the last one to connect, right? Let's see, this one connect is 9. How about this one and this one? What's the value? This is what? 310 and 52. If we do that, that would be 8 plus 2, that would be 10. Am I seeing what you're seeing? What I'm seeing is the point that each one make is the best I can do. So it's like greedy. So for the first point, it doesn't matter which one is the first point. Like this is, let's say this is the first point, and it has to connect to the shortest, right? Because we can say, if I don't connect to the shortest or connect to the other one, then these still has to connect, right? Yeah, think about it this way. Let's think about the last one we connect. Let's say this point is the last one we connect, which means we already find, let's say we already find a way to connect the remaining points. And we can do that because connecting this does not affect any of the others. Oh, actually it does if connecting this creates a loop. But because this one we haven't connected yet, so no matter where we connect, it's not going to create a loop. So let's say we have something already connected. Now we have the last one we want to connect. And we want to make the total cost the minimum. So the best strategy to do so is to connect to the point which gives me the shortest, the minimum cost. That's why this one is the minimum. This one is minimum. I mean, it depends on how you see this, right? Depends on how you see this, because this one we can decide on. What if we want this one to connect? Let's say all the rest is connected. That's not gonna work, right? It's not gonna work. So what we need to find is the leftmost, right? we need to find a point that's definitely not going to be in the middle, not going to be like the transition point on this one. So we need to find the outer edge, right? Outermost first, because the outer edge is not going to be serving as a hub. Because this point is not going to be a hub, because this one connecting to this is definitely going to be more costly than this one connecting to the others. So what do we say? We find, let's find the leftmost, so the smallest on the x-axis, right? So we say that is where we start, okay? That is where we start. So for that one to make the connection to the remaining graph, remaining tree, so the best will be you connect to the one that's the closest to you. So we find that's closest to you, right? And then we look for the point that's the most top. Yeah, we'll look for the one that's at the highest, right? Now what we do, we eliminate this one, right? And we'll find the one that's on the top, which has the largest y value. And then for that, we find the closest. So for this one, like we have calculated this one the closest. So we do this, we eliminate. And then we do the most right, right? We do the most right. And then we eliminate it. And then we do the most down. And now the most down, both are the same, right? Both are the same. Let's say if both are the same, then we just skip. Now we do the most left. And the most left this time is this one, because this one's eliminated. So it's this one. So we say this one we need to connect. So remaining, this is the only thing remaining, so this one connecting to this. And this one got eliminated. And we have one left, and that's it. So what we're saying is we're gonna just find the leftmost, topmost, the rightmost, and the bottommost. How do we efficiently find these points in the first place? Well, what we can do maybe is just focus on the leftmost. We go layer by layer, right? We go layer by layer. So this is the leftmost. So we do this one first, remove, and the next one is this, right? And then we just say from this point, we want to find the closest to everybody else, and the closest is this. So we do this, eliminate this one, right? So the next is this, but when we are doing this, if we eliminate this, we won't have these, then that's not going to work because this one needs to connect to this instead of connecting this. So what do we say in this case? What we say is every point needs to have everybody else in sight. Okay? Every point has everybody else in sight. And if we move from the left to right, then this one, let's say, is above everybody. Then we have everybody else that can make the connection. And then for this one, nah, it has to, hold on, it doesn't make sense, right? What if we don't remove? If we don't remove, we keep everybody, then for this thing, we want to find the smallest distance. So everyone has a smallest distance. So what we have, just find the pairwise distance for everyone, right? And then for each one, then the smallest distance must be made. So let's say for each one, we will make the smallest distance. Let me think. So for each point, we have a smallest distance. Yes, because we cannot have two distances. So each point must connect. So what I say is each point must connect to another point that has a smaller distance to him. So let's say this one must be pointing to this, right? But this is not the smallest distance for him, right? So this one needs to connect to another one. Or like this one has this, but this one must connect to the smallest to him, which is this. And this one's already connected, so this one doesn't have to connect to anybody else. And then we do this one. So what I was saying is just find out the smallest distance for every single one. And we might have it. Let's try this. So what we're saying is to find the smallest distance. So we do O(n) squared to find the smallest distance. And this we have, let's call it ABC, right? So A will be 312, B will be minus 25, C will be minus 4, 1. Okay, so we have AB is 7 plus 5. So AB is 7 plus 5, which is 12. AC is 7 plus 11, that's 18. And BC is 4 plus 2, that's 6, right? So what we want to do is for each point we find the smallest. So for A, the smallest is 12. For B, the smallest is 6. And for C, the smallest is also 6. So, but B and C, they share, right? They share. So what we're trying to say is we need to find which one do we share. How do we find out which one we share? We can just have, A to B, that could be a tuple. So we can say, okay, now A need to find is 12. So we have A to B, right? And then B, we need to have 6, so 12 plus, and then B to C. B to C has not been done before, so we have to call BC, and then plus 6. And then C is to B, and C and B is already in there, so we don't count again. So this one gives us 18. So let's just one more time. Right? One more time. So we can go, right, pairwise. Right? So pairwise, so A, B, A, C. Anyway, so we can get the smallest for A, right? And when we get the smallest for A, we can put it into it already. And then for B, we know the previous smallest, right? And then we can say B, C, B, and then we can find the smallest for B, right? And then for C, since I already done BC, so we cannot do BC again. So we have to put those into, how can we make it easier to find the smallest for each point? Smallest for each point going out. I can just, let's say, from A, right? And we have BC, whatever. And then from B, we have everything as well. So now after we build this, this will be a giant table, 1,000 by 1,000, right? So 1,000 by 1,000 table. And after we build it, we'll just go through every single one to find the smallest, put it into this. Okay, I'm going to try this method, but I feel like this should be a, let's say, more efficient method for this. It's just that I got a gut feeling that this should be a more efficient one. Time-wise is going to be O(n) squared. I don't think we can escape O(n) squared. And since the size is 1,000, it seems to me that O(n) squared shall be sufficient. All right, so what do we do? We need a dictionary. Let's call it dists. Okay. Let's do a default dict. Yeah, default dict, and then we're gonna call it a default dict of list. All right, and then we say for I in range, let's give it n equals len points in range n, j in range I plus 1 to n, right? And then we need to compute their Manhattan distance, right? So what do? We say d will equal to ABS points I, 0, minus points j, 0, that's x, plus ABS points j, now I, 1, minus points j, 1. So that's the Manhattan distance. And then we say dists, I could just call I. Ooh, use default dict. I could have just used a 2D array. Yeah, I could have just used 2D array. Hold on. So dists equal to something for this in range n, and that has to be a what? So each row shall be a this, right? Just a list. So we just say dists I dot append. It's going to be a tuple of distance, and we put j into it, and dists j dot append di, right? So blah blah blah. We finish, and then we say paths equal to a set, okay? And we say for I row in dists, enumerate dists. Okay, do we need I? We don't need I. Oh, we do need I. Okay, for I row in dists, then what? Then we say row dot sort. Right, it was sort based on distance, and I will pick the first one, and we say we'll pick the distance and we pick the other one. So we say A shall equal to the minimum of I and a row 0, 1. Okay? And B shall be the maximum of I, row 0, 1. So we need the order. So this is the order. And we say if AB is not in paths, then res, we have a res plus equal to row 0, that's the smallest. Oh, why do you sort it? We just need the smallest. Wait, can we do smallest that way? Hold on. That's a good question. What if we have multiple that have the same value? That's a good point. What if we have multiple that have the same value? Well, what do we mean multiple have the same value? If we have some that's already connected, and then, yeah, let's say we have a point, and have multiple is also all minimum, then which one should I connect? Well, it's fine. It's fine because that one is considered connected, so the other one will connect to it if it is really the smallest for them. So it just means we don't have to care. I think we don't need to care. We just need to get the minimum, right? If the minimum for a point that's been used before, then we don't have to use it again. If it's not being used before, like multiple, then we can connect this. That's fine because, oh, is that fine? Is that fine? Because if I have connected to someone already, and then I am not a target, then that just means, yeah, I shouldn't make. If I've already made a connection, I should not. Hold on. Let me think again. Let me think one more time. Because it could be, for me, they are the smallest, but for somebody else, they have even smaller. So if I include those, then that will have two paths, while we could have not have two paths. So then what if I have a starting point? Maybe we shouldn't go row by row. We should still follow this through. Let's say we go from leftmost, find the smallest. So we know this one only has one, right? So we find the smallest. And I go here. If its smallest is already found, then we don't do it. Like, who is already, like, are you already in it? If you are already in the network, right? If you're already in the network, then you should not try to add another one. Because if you do, if you add another one, you're not certain if that one added is going to be the smallest. You see what I'm saying? So, and we want to guarantee a way of iterating is always going from, because if we're going left to right, nobody will be connecting to this. There won't be one connecting. Because everybody connecting to it will be longer. So we do this one first. And then we're jumping here. So everyone connecting to this, right? So like if it has only one, it has only one, it might have multiple. It might have multiple connections to make. And what do we do? Yeah, I can see how this one can have multiple but the same. Do we just not do a point when they have multiple? Well, if it has multiple, it has to pick one, right? Then we might create a scenario where it's actually bigger because we do. Hold on. Let me think again. So if this one is smallest connected this. If I have a choice to make, I either connected this, I connected this. And make the connection, right? And then this one is done. So this point of view, I connect to the one that's smallest to me, okay? And then for this point of view, I connect the smaller to me. This point of view, I connect the smallest to me. And for this point of view, I connect the smallest to me. So this all makes sense, but what if for a point of view, I have multiple that has the same distance to me? Then what do I do? Like, which one do I connect? Well, ideally, if you think about all those, if they're already like connected, and for me, it doesn't really matter which one I connect. All right, I can connect to this, I connect to this. It doesn't really matter because they are already connected. So it doesn't matter which one I connect. Okay. But it will matter when we finally compute the difference, right? hold on, if I connected this, right, but this doesn't connect back, this connected something else, which is fine, right, which is fine. But right, I want to connect to one of, so I connect to this one, right? So this one, if I connect into this, and this doesn't matter, but this one I connect into this, right? And this one I connect into this. Now we form a loop. Now we don't want a loop, right? We don't want a loop. So what I say is, if I have a node connecting another node, and then we put this one into it, right? So we know that these two are already being connected. And then for me, right? For me, and then I'm looking for me connecting to someone, and I say, if that has already been connected before, so I just don't connect it. If so, we just go through to the smallest. We try to find the first one that we have not connected, right? We're trying to find the first one, smallest, the first one that has not been connected. Does this make sense? The first one that's not been connected, right? If I've been connected, then I just don't connect, right? You know, I can have that. That's the thing, and somebody has to connect to me. If I connect to you, you connect to me. Right? If we have another point, and that has to connect to one of us. And if it connects to one of us, it will connect to the other. So it's the same thing. Like if everything is already connected, I just need to connect into one of them, and then the rest will be connected. So if I sort, right? But what if I already connected before, and can I connect it to a new one? So that's my problem. If I can I connect to a new one? So the ideal is I don't connect. If I connect it to a new one, but this one doesn't connect back to me, and this one, yeah, from this point of view, if I go this first, then I will make this connection, that will become a loop. So I need to go through the entire thing to see if they have been connected before. If it has not been connected, then I make the connection. If it has been connected, then I do not. And if I have multiple the same, then I simply make, I just make the hold on, maybe we can make this one, right? We'll have this, and then let's say if not dists I, right? Then let's make it into none. So if not dist I, or d is smaller than dists I 0, right? That means we need to swap new things. So we say dists I shall equal to new d and j, right? This if this I, let me say elif d is equal to dists I 0, then we say dists I dot append. Oh, it's basically just this. We're gonna append it, and I'm gonna do exactly the same thing for j. So it's not j. Oh shoot! Do this j. So if this j, if not this j, or d is smaller than this, then we just put a new thing in. Otherwise, we do this. So this can guarantee that after we go through everything, each disk is leading to the same value, so we don't have to do this, right? So everything is the smallest value. So we basically just go through, so for each row, right, each row, we go through every single one, right? We go through every single one to see if they are already in the path, right? If they're already in the path. How do we do that? We can make the path, we can push both in, so it'll be easier to handle. So I don't have to check the min and max. That just feels stupid to me, don't you? Right, that feels stupid to me. So what we can do is we just go for for D and J, right, in row, right, in row. So we can say if ij is in path, then we break, right? Then we don't do anything. We don't have to do anything, then we break. If they're not in, right, else. So we go through every single one, DJ, all the D's are the same. So we go all through the J. And we say ij is in path, right? So this one has been done before. Then we just, we don't do anything. We just move on to the next one. If we go through the entire thing, we have not break, then that means none of them are in, right? If none of them are in, we'll just pick one. Doesn't really matter if they are not in, so we just pick one. So we just say res plus equal to row, right? Row 0. Doesn't matter. Anyone. Row 0, 0, right? And then paths.add I row 0, 1. And then we're going to add another one. Paths.add row 0, 1, and I. Okay? So if it's in there, otherwise we just try to add, and eventually we say result will be the minimum. All right, so let's see. We have 10 minutes, so if this doesn't work, we'll have to check the answer. I am not confident on this one. Come on, it has to work. Otherwise we'll check the hint. But since only 10 minutes, we might just check the answer first and then check the hint. We don't have time to mess with this. Oh, shoot, what the hell? If not or D smaller than dists I 0. Oh, 0. If D is 0, 0, 0. All right, so pass it here. Let's hope I can pass everything. Let's see, let's give it a shot. Runtime error. 0, 0, a single point. Huh. Interesting. What is 0, 0? What is 0, 0? It should be 0, right? int object is not subscriptable. Of course it's not, because I did it wrong. None. Let's do this. Elif row. Has know the syntax. Else, I'll just say if row. Then we'll do this. Okay. Let's give this a shot. Try it again. Yeah, we have a wrong answer. What the heck. All right, so we have to let's get a solution, and I'm gonna think about it later. So let's just find a solution, copy and paste it, but try not to look at it. Okay, let's try not to look at it. We didn't have time, so I just the solution. Not looking. All right, we run the code. Now we cannot look because it's too much. So we just this is an official solution. Official solution. We already see the most important part. I just want to keep it going. All right, let's go back here. Delete the whole thing. All right, so we saw the key piece, but we didn't see too much. So let's just analyze. So I want to pass 6 test cases. Wow, that's too bad. Oh, yeah, apparently that's not correct. Okay, what was the solution to this one? Expected 53. So what I think is probably some has not been connected. Let's see. 2 minus 3, minus 18 minus 8 over here, and 13, 8 over here, minus 17, minus 15 over here. So 4. So the shortest, this will be what? This will be 7. I have 7. And then we say we want this. So that's minus 17 minus 8 to 2 minus 3. That's what? 19 plus 5. It's 23. Right? 23. And this one is going to be this to 17, 13, 8. So that's 11 plus 11. That's 22. 45. 50. Something is not right. Do it again. So this one has 7. That's correct. And minus 8 to 2. This is 5 plus 19. That's 24, not 23. 24. How did I get 29? What? So we have 22. So this to this is 22. Okay, let's put this 0, 1, 2, 3. Okay, and then we have a 7. 1, 2, 3 is 7, and then 22 is back to 0. This is back to here, and then how about 3? So what happens is 1 and 3 share and 0 and 2 share. So which means after we're done, we have not connected everyone. So we need to connect everyone. So we have this, they're all connected. But the 0 and 1, 0 do not find 1. Yeah, so this just means you cannot find the smallest. Because if you find the smallest, it can prevent you from connecting to the others. Then basically what we can say, it is, we have two cliques, right? 1, 3 belongs together, and 2, 0 belongs together. So we just need to find the smallest distance between these two. So basically, we need to find the smallest distance from 1 to 0 and 1 to 2, right? Or 0 to 3 to 0 and 3 to 2. How do we reason this? How about this? We know that smallest distance must be used. It's a guarantee. We have to use the smallest distance. But once you use smallest distance, it might be that everybody is grouped together. Or it might be that some are not grouped together. So the task is after we go through everything, we need to check how many groups do we have. And we need to connect those groups. That's union find, I guess. That's where union find comes into play. For anyone, right? For anyone, we know it must connect to the one with the smallest distance. Okay, so we connect to the smallest distance, and they become a group, right? And then one is already done, right? Then we go to the next one, and we want to find it with the remaining, right? So we find it with the remaining, and we see what is the smallest distance. And if that smallest distance is already in the group, then we end. So that clique is done. So we don't keep extending. So basically what we're saying is that we find a point, we find its closest, and from there we find its closest. From there we find its closest, right? As long as its closest is not within this group, we keep going, right? We keep going until for one of them, its closest is inside this group. So what do you mean its closest is inside the group? Well, what I mean is its closest, it could be outside the group. Well, how about this? As long as its closest is outside the group, we just keep going until we hit a one that all of its closest are inside the group. Then we know we hit the end. So that's the end of that, right? So we have this group that's completely done. And then, right, then for the remaining, right, and for the remaining, so we have this whole group, and yeah, then we form the one, let's say one clique, and then we need to add new things into this group. So the new things, we will do the same, right? We'll do the same. So we find it next. If it's next is, if the next is inside, so okay, so what you're saying, we'll create a group, and then we find the next one. If it's inside the group, then we just add it into the group, and then look for the next one. I see the next is it inside a group? If it's in, we just connect in. If it's not inside a group, then hold on. So we find this, okay? Then what's the systematic way to do this? The systematic way, you just, you build a chain, okay? I can build a chain. The small chain, the long chain, doesn't matter, we build a chain. And after we build the initial chain, then we set aside, right? Since we build initial chain, we set aside. And then for each one, we try to see if is this in the chain, or its smallest is not in the chain. If it's not in the chain, then we'll build a new chain, right? We'll build a new chain, and we're trying to find the next one. If it's inside, then this will belong into the same one. If it's not, then we just keep building the new chain. We'll keep building the new chain, keep building until this entire chain is built. Okay? This entire chain is built. Now once that entire chain is built, then the job is to merge this chain and the original chain. How do we merge? Now what if it has to connect into the new one in order to merge? All we set aside. Okay, we set aside. But does that mean every time we find a new one, you have to go through this thing? I can say if it belongs to a chain. Okay, we can build a chain so they both belong to the chain. Okay, so they both belong to the chain. And then we look for the new one. Yeah, so we build the first chain, right? Now we remove these two. And then we go through this one by one. So every one come out. And we find its closest, right? We find its closest. And then we ask if this one belongs to the chain. So we see if it's none, then we build a new chain, right? And then we put it in. Okay? Then we go for the next one. Right? We go for the next one. Go for the next one. I'll go for the next one, okay? So the next one, again, we find the smallest. Now, if it's smallest, it's already in the chain, then we just group into that chain. Then we're done. If the smallest has no chain, then we create a new chain. Push in there. Then we'll have multiple chains, right? And yeah, we'll have multiple chains. Hold on. So you're saying for each one, and we have a list of chains, right? So we put a new chain, put it in. and then the new one. New one, so this and this. So if this, so for each one coming out, we will go through to see if he's in any of the chains. If he's already in the chain, yeah, it doesn't really matter. So if the new one come out, we find its smallest. Okay? New one come out, we find its smallest. And then find the smallest, and then we say, what if you are in the chain? I'll think again. So we have a bunch of chains, right? So I start with the first one. We're gonna keep extending to build a chain. Again, everybody must connect to its closest, right? So, and you connect to both of them. How about we just connect to one of them? Okay. Smallest, oh man, smallest distance to this chain. If I found the chain and it's self-contained, right, then and go for the outside, that means we need another chain, right? It's also self-contained. Does that make sense? Because this chain is self-contained. We know this is smallest to this smallest is to this smallest to this, and this smallest is to this, right? This is kind of, they're all the smallest. So that's just by themselves because it just cannot, it doesn't want to, because it cannot connect outside. So now we're looking at it on the outside. So we know this must be a chain onto itself. Now we can go over the remaining, right? Remaining we can do, but what if its smallest is into? What if this one's smallest is into the original chain? So we can just say for that one, if its smallest is into the chain, then we just put it into the chain, right? Now, what if we have multiple? Oh, even though I know the key, I still, let's take a look at the hints. Each pair of points with a weighted edge. Huh. Okay. Bless you. You want Dijkstra it? But Dijkstra is the minimum cost from one to the other. That is Dijkstra. We go from 1, let's say from point 1 to point B. Well, then now I would just probably go this instead of doing this. Alright? Because these two, 0, 0, and 310, that'll be 13. Oh, this is also 13. Minimum spanning tree. How do you do minimum spanning tree? Minimum spanning tree. Well, that's long. Mm-hmm. Okay. crossing edge of minimum weight is yeah, it should be minimum, right? That's what it means. Given any cut in edge-weighted graph, crossing edge is MST. Minimum weight. Yeah, so minimum weight. Yeah, I have realized that the crossing will be the smallest. Actually, crossing will be the smallest. Minimum weight crossing edge must be in the tree. Crossing edges separating gray from white are drawn in red. Colors black all edges of any connected edge-weighted graph starting with all edges colored gray. Find a cut with no black edges. Color its minimum weight edge black. Start with all edges, so all edges are this. And then starting with all edges colored gray. Find a cut with no black edges. So let's say we hold on. We say this and this are two disjoint, and then we're going to find the connecting, and then we color this one this, so these two are connected. Now what? Now I find these, now connect this. Now I find this, connect this. Now what will we do? Now we have these and these. So these are, so we connect this, and then this and this will connect this, and the rest connect this, and then connect this. how do we identify it as ineligible? Well, I mean, we can change its value, right? So we put all the edges, right? We're saying we put all the edges onto the priority queue, okay? So we put all the edges onto priority queue. Then we pop the first one, which is the shortest. We know it's definitely going to be there. And after that, what we want to see is whose 7 is going to connect to, or what's 0 going to connect to. Think about these two are the current tree, and all of the rest are the outside. So we want to find the smallest to this. So the smallest has to start with 7. So 0, 7. We can do that, and then we can change it, right? So we can change its value. So what we need to find is all the 7, right? All the 7 leading out, all the 0 leading out, and we need to find the smallest one. Okay, let's say we look and we find out that 7 the smallest one is this, and if it's 0 the smallest one, not this is this, and this smallest, so we put this one in. Now we have to go 170. Alright, and then for each one we need to find the smallest, and then we add it. And then we need to go this, find the smallest. Alright, so basically this just means we put zeros onto it. 0, 2, 0, 7, 0, 4. And then we find the smallest, we know the smallest, and then we can pop it, right? Because we don't need this one anymore. We can pop it. And then, because zeros are all in there, So now we add all the 7s into it. And then we have the smallest, and then we pop it. Right? Then we add all the 1s into it. And then we pop this. Now we have this, now we pop this. Then we add all the 2s that's into it. Right? We'll add all the 2s into it, and we'll avoid that the 1's already added. And because 7, 5 is already in there. Ah, I see. Okay. Okay, I see this algorithm. I see this algorithm. We can pop. Yeah, we can pop. So every time smallest, we just pop. And then we keep adding, and keep popping. All right, what's this eager implementation? Delete ineligible edges. And it contains only the crossing ones. Minimum edge from each non-tree vertex to a tree vertex. When we add a vertex v to the tree, the only possible change with respect to each non-tree vertex w is that adding v brings w closer than before. We do not need to keep on the priority queue all the edges from w to vertex tree. We just need to keep track of the minimum weight edge. Okay, we keep track of the minimum weight edge and check whether the addition of v to the tree necessitates that we update that minimum. Enjoy. Update. Because the edge VW now has a lower weight, which we can do as we process each edge in adjacency list. One edge for each. So for each none, we maintain one. Right? We maintain one. So once we push this in, we just check. If this to this the distance is smaller, then that one we can remove that one. Is that what you mean? So we have all these, that's the initial, Okay. Now we add 7 into it. Right? We add 7 into it. So after we add 7 into it, we have 7, 1, 7, 2, right? So we have all these are the edges to 0. Now we add 7 into it. So the question we want to ask is among 7 to everybody else, who is the smallest? I say this is the smallest, so we push this one into the priority queue. Wait, hold on. No. So 2, originally we have 0.26, right? But now when 7 is into it, when 7 is onto it, we say whether it make it shorter, right? So we know, okay, we have 0 is inside, and we have everybody else, all right? So 0, 7 we can pop. This one doesn't mean anything anymore. So we go through the priority list, right? We go through the priority list. We check, okay, we now know because 0 is in it. So we say 2 is outside. Then we say compare 2, 7 and 0, 7. And then we find out 2, 7 is, why you put 2, 7 in it? Shouldn't 0, 2 be still in it? Yeah, 0, 2 should still be in it. I don't quite understand, but here's what I would do, right? So we do this after we add a new one. We go through the priority list, right? We go through the priority list, and then if anything, if adding this brings it closer, so we just swap. Instead of to 2, we swap to 7. We change its value, right? We change its value, becomes 7. And then like 4 to 0 is 4 to 7. So basically we did 4 to 7. We don't no longer do 4 to 0, because 4 to 0 will no longer be useful, right? So 4 to 0 will be eliminated, and 4 to 7 will be put in, right? And 6 to 0 will still be in there, because 0 we don't have from 0 to 7, right? So this one will still be in there. This one will be updated. 0, 2, 7, 2 is bigger, so it doesn't change, right? So I go through this. Now, what's the difference between this and this? We have all the zeros in it, right? And then we do 7, so everybody connect to 7 need to be put into it. And then we have 2, 7, and we have 0 to 2 as well, right? And then we put 1 in it, we have to do all the 1s, which is just 5, 1, and 1, 2, and 1, 3. And then we'll do 0, 2, right? So okay, we'll do 0, 2. So once we do 0, 2, what we're saying is everything that connects to 2 become obsolete. Anything connected to 2 will become obsolete because 2 is already in. So basically this just means if anything 2 pop to the front, we can just ignore it. Now 2 will be 3 and 6, right? And the next one will do this. So anything connected to 3 will be obsolete. Originally connecting 3. And 3 has 3, 6 to load. Then 5, 7 becomes the top, right? And then 1, 3. No, just popping it, right? I think this is to create a, maybe just create a new adjacency list every single time. No, I think this is to try to find all the edges. This is so we can keep the original edge. We just add new edges, right? We add new edges, and then what we just say is if we have 2 nodes already in there, then their connection can never be part of it. So we just put a set of all these, and then if anyone, if both are in it, and this one just got taken away, and if one of them is not in it, then we take it. So like this one will be 5, 7, right? And then 1, 3 is in it, 1, 5 in it, 2, 7 in it, but 4, 5 is not in it. So we add this, right? And then we add this, basically add 4, So we're going to do all the 4 as a not inside, which is only 6 left. So we do, we add wait, hold on. Oh, this step we add 3, we add 6. Right now, this is the smallest. So we add 5. Oh, 5 we add 4. Right, we add 4. And then after this, 2 and 6. Right, we add 2 and 6, add 6 and 4. And then the remaining, they're all gone. Okay, I can code this. One more. Let's go through the last one. Okay, 0, 7, 2, 3, 1, 7, 0, 2, 5, 7. Now after 5, 7, so after 5, 7, we go to 1, 3. But we cannot do 1, 3 because 1, 3 is already in it. Cannot do 1, 5 is in it. Cannot do 2, 7 is in it. Next one's 4, 5. The union find to identify those that causes cycles. Wait, how do you use union find? Why do you need union find? Why can't you just why can't we just use a set? Instead, we need to use a union find. Okay, we have a priority queue. Consider the edges in order by weight. Okay, we take the smallest, so they must be union. And then we take the next 1, 2, 3, they will be in a union. So we just say they will all be together, right? Causes the cycles. So we have a new edge. How do we know if the new edge coming in will cause a cycle? Because we say 1, 3 is already in it. Right? If the new thing coming in has an edge on the outside, 1, 5, 2, 7, 4, 5, 1, 2, 4, 7, 0, 4, 6, 2, 3, 6. I don't understand why a union find is necessary. Can we just put all the union find basically say we union those with union, and then with a new one, we can try to union them, or we can try to see why a set will not work. We just check it twice. We check the first one, see if it's in the set, then check the second one if they are already in the set, which means they are already connected in a certain way. Hold on, let me think again. What if 0, 2, 0, 7, 2, 3 1, 7, 0, 2. That's why you need, because if you use a set, after this, you say 0, 2, that will already be. You say, okay, 0 is in the set, 2 is in the set, so you cannot connect it, but in fact you can. But union of set, we can put this as a union. So these form a union, right? If this forms a union, then we say we want to put 0 and 2 in it. And then we can say, wait, then how do we know that it's union? So we say these form a union. And 0 and 2, if both belongs to one union, then that will cause a trouble. Okay, so we say 0, 7. So we form a union here, all right? And then we have next one is 2 and 3. And we say 2 and 3. So 2 is a union here, no. 3 is a union here, no. So 2, 3 form its own union, right? So we have 2 unions. And then when I was 1, 7, and then we check. Is 1 in any of the union? No. Is 7 in any of the? Yes. So 1 belongs to this union. And now we have 2, 3, 2, 2, 0. And then we say 0 belongs to this union. 2 belongs to this union. So now we can just say, we can union these two, right? We union. And next, 5, 7. Is 5 in or is 7 in? And then we have, and how do we combine the two union into one union? I need an implementation. Krushkal, that's the one I was looking for. Try joining both nodes of the current edge if the nodes are already connected. Wait, hold on. Try joining, so I want to join in both. If the nodes are already connected. I don't understand. About join. Hold on. What does union find do? Union find is to union these two to create a connection between these two, right? So within the union find, join these, you can join these. And then if they are already connected, which means if we say join, we'll return false to tell us that it has already been joined. I think now I know. So I got confused what union find does. I thought I need two union finds. No, it's one union find. They will be identified by their rank. Okay? So with the union find, if I have two, right, they have to be connected. And they have to be connected. So we use union find to union these two together, right? So we union these two together, which is fine. And then I have new two nodes, want to union them together. And the thing is, every time we union, they are all connecting together. So if we have two nodes that's already in one union, and I want to union them, then they will return false because we try to find a group. We will find, and if they have already belonged to the same group, then we will break out. So that's what this means. That's what this Kruskal algorithm. So union find to identify cycles. So if they have not been unioned together, so which means they do not have the same rank, they have different rank. If they have different ranks, then we can union them together. And if they have the same rank, that means they are already unioned together, so we cannot add. Wow. This is some stuff. Huh. Well, I'm completely out of it. Minimum, I think this is the first time. Minimum spanning tree. This feels a difficult problem to me. I mean, if you know it, it's probably not difficult, but prims. Owen squared. All right, so let's implement one of them. Well, never done a minimum spanning tree before, so it is understandable that I cannot solve this. This is the Gauss algorithm. All right, so we need a union find. Yeah, we're gonna implement union find right here, and then once we do that, I'm going to read the other solution. So we have disjoint set union. Okay, so I want to find a whole list, right? Dists for, we do need points, range n, j, range I plus 1 to n, right? So we have these two, and then we say points distance equals, we shouldn't delete this one. Yes, points I zero, j zero. I1, J1, right? So we do this, we get a distance, and then we just need to append one of them. Say this dot append, right? D first, because we need to sort it, and then I and J, right? And then when it's done, we say dist dot sort, and then we say DSU equals DSU, union find equals DSU, okay? DSU what? I think I need n numbers, so we just say len, no, numbers n, okay? Then what do? We just go 1 by 1, right? Less equals 0. We just say for distance I and j in dists, right? So if union find dot union, right, with a union I and j, if it's true, then rest plus equal to d, right? And number of edges added. Num edges equals 0. No, num edges should be n minus 1, right? And say num edges minus equal 1. And say if not num edges, I'll use return res. Break. There we go. It is easy, huh? Using this method. Okay. Yeah, once you figure it out. Well, this one, curso, I can understand. All right, anyway, so I'm going to end it right here, and I'm going to have to keep reading through this thing. and I should add it to the list. This is a very good problem. My God, nightmare. This is a nightmare. Minimum spanning tree. Very interesting. All right, that'll be it. I'll see you guys tomorrow. Adios.